In this lecture, we're going to talk about three new stuff, which is saddle point, max min, and min max. But let me first mention that the content of this lecture only apply to two-person zero-sum game in matrix form. So let's now talk about the first new word, which is the saddle point. The saddle point is basically the entry in the game matrix that is the smallest in the row and largest in the column. And we have the first principle that says, well, if a game has a saddle point, then both players should play a strategy that achieves it. So if we look at the example from the last lecture, we kind of see that all pure strategy Nash equilibrium that we have here are indeed the saddle point. If we look at number 3 here, this is indeed the smallest in the row and then largest in the column. So number 3 here again is smallest in the row and then largest in the column. So this is a saddle point. If we look at the next example here, number 1, this is the smallest in the row and then largest in the column. So once again, this corresponds to a saddle point. And then in the last one, the number -1 here, this is the smallest in the row and it's kind of greater than or equal to the things in the column. So this guy is once again a saddle point. And in case you are not familiar, a saddle is something that you were to sit on if you were to ride a horse. Now, for a 3D graph, a saddle point is something that looks like this. It is actually a place when the derivative for in terms of both x and y are gonna be 0, but it's kind of neither the relative min or relative max. And if you look at it from this way, it will look like a relative min. But if we look at it from the other direction, it's gonna look like relative max now. And this is kind of what we see earlier as well. It's going to be a minimum in one direction and a maximum in the other direction. So if we were to look at the examples that we have for this lecture, so let's look at the example of 8.1 that we have here. So which one of these are going to be saddle point? Well, we can just check real quick. This number 1 here, is it the smallest in the row and largest in the column? So if I look at the row, it's gonna be the pink thing, and the column is gonna be the blue thing. And we kind of see that, well, number 1, this is the smallest in the row, but it's not the largest in the column. So this number 1 here, it cannot be the saddle point. So you can kind of look around a little bit. So let's say if I move here, so does this number 5, could it be a saddle point? Well, it's not the smallest in the row, so this is not a saddle point for sure. So you can kind of chase around a little bit, and in the end, you'll find that this number 7 here, this is the saddle point because this is the number 7 here. This is smallest in the row, and this is largest in the column. And if we continue, so which one of these are gonna be our saddle point? So let's kind of see. If I look at the number 1 here. Well, this number 1, this is not a saddle point, even though it's the smallest in the row, but it's not the largest in the column. So we can try to look at number 4 here instead. Now, number 4, this is not the smallest in the row, so it cannot be a saddle point. So let's try number 2. So number 2, this is the smallest in the row, but it's not largest in the column, so it cannot be saddle point. And then if I try this number 3, it's not the smallest in the row. So well, we try out all the possibilities, but none of these are saddle points. So this game, in fact, has no saddle point. Okay, so that's the first new terminology that we have. Now the other two, which is going to be the max-min principle and the min-max principle. So, the max-min principle said the first player should choose a strategy that guarantees the highest payoff. And the min-max principle said that the second player should choose a strategy that guarantees the lowest loss. So let's try to see this in the next example that we have here. So let's put ourselves in Alice's shoes for a moment. So this is Alice. So she's choosing between the first row or the second row or the third row. So she's choosing between one of the 3 options here. So let's say if she chooses S1, let's see what's gonna happen. Well, Alice's reasoning would be that if she chooses S1, she will either get $1, $2, or $3. So if she chooses the first option here, that will guarantee her that will guarantee her. That will guarantee her $1. So notice how this number 1 here, this is basically just the minimum of all the numbers that we see here. It's going to be just the minimum of 1, 2, and 3. Yeah, so choosing the first row, it guarantees her $1. Now, if she chooses S2, yeah, what about the second row? So if she chooses second row, she will either get $4, $5, or $6. So choosing S2 is going to guarantee her $4. So once again, this is the minimum of the 3 numbers, which is 4, 5, 6. Well, how about S3? Choosing S3 is going to guarantee her $7 because she will either get $7, $8, or $9. So this is going to guarantee her $7, and this is going to be the minimum of 7, 8, and 9. Now, well, if we put ourselves in Alice's shoes, and we can do this reasoning. Well, if she chooses the first row, that will guarantee her $1. If she chooses the second one, that will guarantee 4. If she chooses the third one, that will guarantee 7. Yeah, and Alice like bigger number, so she should choose the last strategy here, which is S3, because that will guarantee her the highest payoff. Notice how what she does is that she takes the minimum of the number in each row, the minimum of number in each row, the minimum in each row, and then she look at the maximum available minimum number. So let me actually make this pink. Okay, yeah, so she look at the minimum number from each row, and then to make the decision, she just have to pick the highest number. Now, if you have taken the OR, the operation research before, you probably are familiar with this kind of max-min thing. If I were to write that as a matrix form, it would look something like this. So my entry, let's call it A11, A12, A13, and then A21, A22, and A23, and then A31, A32, and A33. So this is gonna be the first row, I is 1, and then this is I is 2, this is I is 3, and then this is J is 1, J is 2, and then J is 3. So when Alice has to choose between the row, what happened is she kind of fixed the I first. She let I equal to 1 and see the minimum between these 3 guys. She let I equal to 2 and see the minimum between these 3 guys, and then she let I equal to 3 and look at the minimum between these 3 guys. Yeah, so what happened is she is looking at the minimum of Aij when she let the J run and she let I fix, and once she did that, she looked at the maximum between the minimum number. So this is the notation that the you might probably have seen if you have taken the OR. So this is from Alice's perspective. Let's try to do the same reasoning, but from Bob's point of view. So from Bob's point of view, well, again, Bob is gonna choose between the first column, the second column, or the third column. Now then, the min-max principle is gonna say something a little slightly different, because the second player, which is Bob, should choose the strategy that guarantees the lowest loss. Notice how the number that we see here, this is Alice's payoff. So Alice is gonna get between like $1 to $9, and then Bob is gonna be the one to pay Alice. So for Bob, let's kind of see his reasoning then. So if Bob chooses T1, so let's say if Bob chooses T1, so what that means is he's either gonna lose $1, $4, or $7. So Bob's reasoning would be that if he chooses the first column, he's gonna lose at most 7. Yeah, so he's gonna either lose $1, $4, or $7. So in the worst case, in the worst scenario, he will lose $7. Now he do the same reasoning with T2. So if he chooses T2, well, he can see that he's either gonna lose $2, $5, or $8. So the worst case scenario that could happen is that he will lose $8. Lose at most $8. And he do the same thing with T3. So if he choose T3, you can kind of see that he's gonna lose at most $9. So he's either gonna lose 3, lose 6, or lose 9. So you can kind of see how Bob's point of view is gonna be somewhat different from Alice. Alice's point of view is gonna be somewhat optimistic because she's thinking about how much she could earn. But Bob is gonna be somewhat pessimistic. He's gonna think about how much he could lose. So if we are Bob, then we can kind of reason ourselves that, well, if we have to pick between the three, we can either, well, in the worst case scenario, we will either lose 7, lose 8, or lose 9. So, well, maybe the first option is probably not too bad then, because that means in the worst case scenario, we could guarantee that we're not gonna lose any more than 7. So, this is gonna be the Bob's point of view, which is the min-max principle. Let me actually write where the 7 comes from. So this 7, this is actually the max between the 147 that we see here and the number 8 here. This is the maximum number in the second column. So this number 8 here comes from the maximum number from T2, which is the max from 258, and then this last 9, this is the maximum from the 369. And we see earlier from Alice's point of view that Alice should choose, we said earlier that she should choose F3. And then we also said earlier that Bob should choose T1. And that's because it's going to minimize the loss that he could have. So it's going to minimize the maximum possible loss. So it's going to be the max in each column. Now, well, if we think about it, if Alice choose S3, if Alice were to choose S3, like I said earlier, and if Bob were to choose the T1, like we said earlier, so the value of the game is going to be 7, and this is indeed the saddle point that we mentioned earlier. Now, well, we're going to come back to this in a moment, but for now, let me also write the notation for Bob. So what Bob did is that from the same matrix, he's going to look at the maximum in each column. So from Bob's point of view, he's going to look at each column. So he's gonna let J fix. First J is either gonna be 1, 2, or 3. And then when he fixes J, he's gonna let I run from 2 to 3, and he's gonna find the maximum of that. So the math notation for that is gonna be the max when he fixes J and let I run. So it's gonna be max of Aij over I, and then he's gonna minimize that over the J. And again, if you have taken OR before, you probably might have noticed that these two guys are basically just the dual of each other. But if you haven't, then that doesn't really matter much. Now then, let's take a look at the last example here. So from Alice's point of view, let's see what's going to happen. So Alice could choose between S1 and S2. So if she chooses S1, that is going to guarantee her at least $1. And then if he chooses F2, if he chooses the second row, then that's going to guarantee her $2. So what we can kind of see that the second row is going to be better than, so that means she should choose F2. Okay. Or we can also say that the maximum value is going to equal to 2. How about Bob? What if we look at this from Bob's point of view? Well, Bob is going to have to decide between T1 and T2, and if he chooses T1, we can see that he is going to lose at most. Well, he's going to lose at most $4. Because in the worst case scenario, he's going to lose $4. Now, if he chooses T2 on the other hand, he's going to lose at most $3. And that's because, well, if we choose T2, notice how he'll either he'll either lose $3 or $2. So in the worst case scenario, he's gonna lose $3. So if he can pick, if he has to pick between the two, for the first option he could lose $4. For the second one, he could lose $3. So the second option is gonna be a better choice here. So he should choose T2. He should choose T2. And then that means the min-max value is gonna equal to 3. Notice how in this case the two numbers that we have are actually not the same. The max-min value come out to equal to 2, but then the max-min is 2, but then the min-max value come out to be 3. And this is going to relate to what we have earlier here. So the max-min and min-max value are going to be equal only when there is a saddle point. So the max-min and min-max are going to equal only when there is a saddle point. And when that happens, that value is going to be the value of the game. And then the pure strategy match equilibrium is going to be just the saddle point. So basically, in the end, what we have is that the four things that we have are actually the same thing. If we have a saddle point, then that's actually the same as pure strategy Nash equilibrium. And when that happens, that will mean that the max-min is going to equal to min-max. So that's going to be when max-min equal to min-max. And that's going to be when we have the value of the game. So that's going to be the optimal play of the game. So that's going to be where the game ends up with. So that's the value of the game. When you have any one of these, you will have all others. And that's kind of what we see in the example 8.1 here. When you have a saddle point, that's going to be the value when the min-max and max-min equal. So you can kind of see how the number 7 here, this is both the min-max value, this is both the max-min value and the min-max value. And that is also the saddle point, and that is also the pure strategy Nash equilibrium. If Alice were to play f3 and Bob were to play t1, then there's no need to change their mind. So Alice, she should not choose any other strategies here because that will give her less money. And Bob should not change his mind because, well, if he chooses anything else, he will lose more money. So this is indeed the pure strategy Nash equilibrium. So the four things that we have here are actually the same thing. And if you look at the terminology that we have earlier, sometimes in economics, they will say things in principle. So it said, so it's kind of not, so it's not a math theorem where, where things are exact. When we have this principle, it only says that the player should do this, the player should do that. So it's kind of like an economic way of doing things. But in the end, even though we have these three principles that say, oh, you should do this, you should do that, but they are actually not in conflict because in the end, they'll end up being the same thing. On the other hand, if you don't have saddle point, then you're not going to have any of these. If you don't have saddle point, that means you're not going to have pure strategy Nash equilibrium. It's not going to be that max-min equal to min-max. So your max-min is not going to equal to min-max. And then you'll not be able to find the value of the game. And this is indeed what we have in the latter example. This is when you don't have a saddle point, and that's going to be when your max-min and min-max is not equal, and then you cannot find pure strategy Nash equilibrium in this game. So if we were to take a look at this for a moment, so what's going to happen if we were to play this game? So if we were to use the max-min principle, it said Alice should choose f2. So let's try to pretend this is going to happen. So Alice should choose f2. And Bob should choose t2. Yeah, so Alice choose f2, Bob choose t2. What could go wrong with this? Well, if Alice see that Bob is gonna choose t2, then because this is not a Nash equilibrium, so Alice could change her strategy because she sees that, well, if Bob were to choose t2, then she could have choose t1 because that's gonna give her more money now. Now she's gonna have $3. But now Bob knew that Alice is gonna change her mind and choose f1. So he can see that, well, why should he play T2 then? Because that's gonna lose him $3. He should instead choose T1, and now he's only going to lose $1. And because Alice is also smart, so she knows that Bob is gonna change his mind. So she said that, well, if Bob is gonna choose T1, then she should actually choose S2, because why should she choose S1? Because that's only gonna give her $1. If she do this, that's gonna give her $4. And it kind of go back and stuck in a loop, because now if Bob sees that, well, Alice is now gonna choose S2, then, well, maybe he should not choose T1, he should choose T2 instead, because that will save him money. Instead of paying Alice $4, now he has to pay Alice only $2, and now we go back to the same place. So it kind of got stuck in a loop. So we're gonna talk about how Alice and Bob should play this game in some other lecture later.